Okay, folks. No. So what we're going to do here is we're going to talk first about the schedule, and then we'll go into content today. Don't make me ban eating. Don't get too distracted. Eating is fun. Not a party time. It's work time. Okay. I know, but you're rotated towards her like you're about to have a conversation. All right. Okay, so the first thing we're going to talk about is the fact that, what happened to the homework? There's no homework this week. Yay. It's because we didn't really learn that much. Everything that we learned is more of like, okay, trying to understand the concepts about history. And then we're going to get into this. You're going to get them probably every week because you have new content. I want to make sure that you really get it. I went to go make this homework and I was like, there's some words in here and there's like a few concepts, but it was contrived. And I had a really bad morning. So I was like, no homework. Okay. Nothing new today.
It's gonna be due eventually,
Well, this one will.
but not the one we did.
The one you did is already due. 2-1 is already due.
I thought you said they were in homework.
This one here that would happen starting today, second homework doesn't exist. So week 1, week 3. Sorry, due today, I mean like there's nothing new that will be due next week's from today.
Okay.
Does that make sense?
Yeah.
Sorry, that was not confusing. Okay. Okay, and then you'll notice here, week 3. Look at that number. Ooh, 99%. You want that on your exam, right? Well, that's the moon phase. So on Monday, we'll have an almost full moon. So we're gonna do another moon lab. I mean, not another moon lab. We're gonna do an observation, hopefully of the moon, noting, of course, that if it's windy or if it ends up being cloudy, that's impossible. And if it's the case that we can't observe that night, we'll just do a different lab instead. Probably the cause of moon phase. But either way, you'll get some moon content, right? Questions? If you have the homework, you can turn that in here at the end of class. You don't have to do it right now. Ways that I like the homework. I got a lot of questions about this, so I guess I should have been more clear. I prefer written homework. Just feels like more personal. And then if you have a chat GPT, you can either copy and paste it and print it out and then write on that paper, or you can write what it said. Either way. Okay. The latter, I think, is a little trickier. Questions? Okay. All right. What's that?
Nothing.
Nothing. Very good. What's that?
Rocket.
Rocket. Good. Which rocket?
That's the rocket.
Yeah, that's one. Where is that? Why is it Florida?
They built it there.
The water.
Could be California.
Yeah. Vandenberg's not on the water.
Is it Kennedy Space Center or is it?
It is Kennedy, yeah.
It's not Houston?
Mhm.
Oh.
Houston is actually not where they shoot rockets. We'll talk about that a little bit later when we talk about forces. But this part here, this happens in Florida because Florida is one of the most southern states. Except for Hawaii. Why don't we shoot rockets out of Hawaii?
People would be very mad at us.
What?
Is the terrain too?
I don't know.
What is-
the weather?
What is different about Hawaii than say like other parts of the US? It's surrounded by water. Takes a while to get there. So imagine that you build a telescope piece, like just the camera, you build that in Ohio. And then you build, say, the telecommunications piece, you build that in Nebraska. Right? You can just, you send those by a train. Getting all that stuff out to Hawaii is really hard. Okay. All right. We're going to talk about that in more detail when we talk about force. Okay, so let's finish the conversation about this. Okay, so which of the following was not observed by Galileo? Is it A, 4 moons orbiting Jupiter? B, stellar parallax? C, mountains and valleys on the moon? Or D, phases of Venus? You ready to vote? Show me your test. So on 3, 2, 1. Okay, so I see a couple people did the reading. What's the right answer?
Well, I know it's not a.
You know it's not A,
Yeah.
because they're called the Galilean moons. Good. Phases of Venus. Okay, so a lot of people chose that. That's not right.
The mountains and the valleys of.
Also not right.
Could be different right there.
Okay, we did it. Okay, okay, so that's why we read the book beforehand. Okay, so who's this dude? Galileo Galilei.
Gal.
He's a turtle.
He's a turtle?
Yeah.
No, incorrect. So in fact, Galileo's observations solidified this Copernican revolution. What was that Copernican revolution in thought? What's that? Yeah, heliocentric worldview. And what were the issues, what were the things, when we think about like a sun-centered worldview and an earth-centered worldview, what were some of the postulates, what are some of the laws that they said for the earth-centric worldview?
Circle orbits.
Circle orbits, right? So they like circles on circles on circles, right? And Ptolemy was like, I can make you extra circles, epicycles. Anything else?
They were in certain order.
Certain order, okay, so but the orders look the same, right, in both of the models? So that doesn't really break it. Anything else? What did they say about the heavenly bodies?
There was this,
They were,
there was kind of this, like,
the celestial sphere was fixed, yeah, but what about the, like, the planets themselves? The surfaces, anything like that?
They're perfect sphere.
They were perfect spheres, right? This idea of perfection, that the heavens should be perfect, is something that they postulated because they couldn't see it, right? They just looked up in the night sky and they're like, the dot, right? How do you know what it looks like? Red, probably a perfect red dot, right? Okay. So this thing here, is this one up here. It's a telescope. And telescopes were invented to look at. No,
Moon.
No.
Moon's up.
no,
Planets.
no,
the star.
Galaxies.
no, they were not invented for this purpose.
Mountains.
Galaxies.
What's that?
Mountains.
No, close though.
Hills.
This- Not
Other kingdoms.
Other kingdoms, potentially other
enemies.
Civilization.
ships.
Civilization.
Okay, so they were invented for looking at other boats. Why would you want to do this? Well, at this time, there's no GPS. There's no like, hello, are you my friend? So what you would do is if you had a little spyglass, you go and you look and you're like, oh, that's an enemy. Let's go fucking bomb them. Okay, this is a great example of technology being led by war, which is a natural human state. And instead, Galileo was like, oh, what if I look up?
Wow.
Well, what happened?
Oh, so in fact, that's what he did. All he did was he took something that existed and he pointed it towards the sky. Okay, and so what he began to see was stuff like this. And look at how great these drawings are. You talk about how bad my artistic skills are. I mean, come on.
Yeah, that's pretty good.
Hey, come on, that's not good. Compare this set of drawing to his contemporary Leonardo da Vinci. Who's better?
Well, Alan, look, our-
Galileo. Yeah, sure, Galileo's not an artist. Galileo's famous for a couple things. Anyone else know what Galileo's famous for? Just as an aside, a tangent.
invention.
What did he recognize?
The ball.
Yeah.
Oh,
Did
the-
the gravity experiment, right?
He couldn't do the gravity experiment. He did a thought experiment about gravity.
The ball.
This is, remember, this is well before Newton. This is well before gravity was discovered as an example.
Ball.
The ball in the hill.
You put a ball and slide it.
Yeah, so you roll it down an incline. And what he essentially said was that objects have an internal property called inertia. So when you think about Newton's 3 laws of motion, which we'll begin to touch on today, there's a 0th law of motion, and that's Galileo's. We'll talk a little bit about how these all connect together later on. So for example, objects have an inherent property that either keep them moving or make them stop. Heaviness. Someone had to think of that. Crazy. Now we just sort of bake it in and teach a child that, and they already know. Okay. So he was one of the first people to turn this Dutch invention to the sky. Not the only one, but one of the first. Okay. And one of the things he saw was that there are phases of Venus. I'm not going to specifically teach you about the phases of the moon. We'll talk about this in a lot more detail when we do the actual lab. But let's think for a moment. Oh, look what I got here. Oh, wow. I got a light side and a dark side. This should be visually straightforward. So what I'm going to say is this side here, the dark side, is the dark side of the moon. And this side here is the light side of the moon. And we always see the same side. It's like that. So if I hold this away from me, great, I see the same side. That's not really helpful. So instead I want to say, what about the side that's illuminated by the sun? And we're going to assume that it's only the shadow that moves. Because when it's illuminated improperly, let's say you're all the sun, and I hold it like this. Now I can't see it, right? You all see the front, I see the back. And if I hold it over here, I can see the whole thing, right? What would you call this space? Full. What would you call this space?
New moon.
New moon. What do you call this space?
Half moon.
There you go. You did it, right? Okay, so in fact, we can tell that the moon is orbiting us because of the evidence of things. So Venus and Mercury, we already said they had some issues with the whole circles on circles, and the reason why they didn't quite move very far away from the sun. Well, they said, well, the epicycles of Venus and Mercury, those are tied to the sun by a magical coincidence. Okay. And there was an important caveat here. Okay. Here's the caveat. Here's the sun. Here's the earth. If Venus orbits us, okay, its phases will look very different than if it orbits the sun. Right? Because it's going around little circles, and then it's going around us. And so its phases will look really, really different. Does that make sense? Okay. So what did he end up seeing? Here's the Ptolemaic view of Venus. There's the sun, goes through these little circles. So you would see, for example, a new, and then a crescent, and then a new, and then a crescent, and then a new, and then a crescent. That's the idea if Ptolemy's right. Circles on circles. And on the right-hand side, if Venus goes around the sun, then you see all of these phases. In fact, you'll see a phase that you never see, which is a phase of Venus behind the sun, while we are on the other side. Right? If we're on the same side, we see this side. If we're on the opposite side, we see that. You can pick these up and show yourself. Right? They're clear or not clear? Okay. Because, yeah.
Is the moon, is the dark side of the moon only getting light during the solstice?
No, so the dark side of the moon gets light. So for example, imagine right now that this is the back side of the moon. What we think of as the back. Okay, so it goes around us. So you're going to be the sun. And currently the back side of the moon is facing away from us. But as it goes around, you see that during the new moon period, the backside faces the sun.
Okay, so it does, yeah.
Okay. We'll talk about eclipses a little bit later. So because Ptolemy said that we had to tie Venus to the sun, couldn't go too far from the sun, and it orbits in front of us like this, it means it's only in this new moon configuration, and maybe it wobbles back and forth. So if I look in a telescope and I see it full, boom, immediately Ptolemy's wrong. Okay. Pretty easy. And sure enough, all you could see was total brightness before the telescope, and then you have the telescope. Now, interestingly enough, I'm going to show you the picture. These are normal pictures, not Galileo's pictures. this is time. Okay. And there's space between. So what two things do you notice about these pictures?
They're partial,
Raise your hand.
they're partial view.
Okay, okay, yeah. It's really hard to get a full view. Anything else?
It looks like it takes 6 months to go from foliage to bark.
This is only about 4 months.
Oh, so the month is better.
Yeah, sorry, these are not American numbers.
It was taken on my birthday.
I think give it another month.
I was born then.
Which one? There's lots of here, so.
The bottom one.
This one?
Oh, that was
That's your act.
Yeah.
6 inch.
Well, now you can crop that and put it in. Okay, so yeah,
Those are,
Yeah.
hold on.
yeah, they're crescent signals on Cupid's feet.
So these are some crescent phases, yeah. There's some gibbous phases, but we can't see them here. Gibbous phases is the one it's the light stretches out on the other side, and there's like a crescent of dark. You're missing two very important things.
It's only like illuminating the right side, I guess.
Yeah, we could keep watching it. We could keep watching it. There's one really obvious thing, and once I say it, you're like, oh my god.
Five.
The size. It's getting bigger.
Oh.
This is larger than this, is it not?
I thought you just said it.
If I didn't do something. If you shot something.
She's getting bigger.
Okay, it's getting bigger
Okay.
because it's getting closer. Okay? Anything else you notice? This one's gonna be, it's gonna be a stupid way of saying the same thing, but it's important.
It's getting large.
Getting larger, good, but what else?
There's more of like a.
Shadow.
There's more of a shadow. Okay? As you go from the here to here. But it also got larger. By amazing coincidence, this fraction almost cancels out. So the amount of light you get from this crescent is almost the same amount of light that you get from this. So the brightness of Venus is almost constant throughout the year. So no one ever expected, because for example, let's imagine that it was a little bit closer to the sun, or a little bit closer to us. Then its brightness would change throughout the year. Because as we saw these different phases, it would seem to get dim and bright, dim and then bright, just like the moon does. The moon gets very bright and very dim, very bright and very dim. We would have immediately known that there were phases. Didn't. Isn't that weird?
So it maintains the same light.
What's that?
It maintains almost the constant light.
Yeah. When you integrate, when you take the total amount of light. Right? So obviously there's less light from right here, but it's longer. You see the total amount of light? And even when it's right behind us, it seems to direct light behind it. Weird. Right? Okay, yeah.
So by that logic, since it's almost like a new moon kind of phase in the middle of the year, would it be like a full moon phase at the end of the year? In like December?
Like a 6-month period.
So we have to remember, we haven't talked about orbits yet. And Mercury moves faster than us. Venus moves faster than us. But we haven't really talked about how our differing geometries work. Remember, they're all moving together. If it was fixed in space, you're right, as we moved around, it would have a totally different view. But it's moving with us. So it's not as easy to just read it off.
How long are the nights on Venus?
Too early for one. Okay, so the next thing that he found, this is the cooler thing that he found. This is the one that has his name, of course. He's looking at Jupiter, as all people do. Pull up the telescope, and he started watching, collecting the stars and pointing them. And he noticed that there are these stars that really like to hang out near Jupiter. Really like to hang out near Jupiter. And they don't like to go anywhere else. And they're moving. So at first he thought, oh, they're planets. They weren't moving on their own. They're only moving back and forth and back and forth and back and forth, back and forth. Oh, that's really weird. You realize they're moons. And if this means that there's moons around a different object, then why is there a preference for everything going around the Earth? Because if moons can go around Jupiter, why are we not going around the sun? Why is Jupiter? Okay. This one here, it began, so if you look at that picture, if you've ever looked at the moon, right? This is sort of baked into your mind already. But go ahead and look at the moon tonight. And tell me if you can see craters. Or you just see different colors. Okay? Just looks like maybe someone did this nice oil painting. You can't actually see the depressions. And sure enough, when you look in a telescope, you can see that there are ridges, there are craters, there are cliffs and canyons. Right? This is all stuff that you can actually see with your eyes in a telescope. Okay. All right. He also saw something that's pretty unusual. The sun has spots on it.
She has some spots too.
It has sunspots too, just like we all do.
Wait, telescope at the sun?
Yeah.
That's
Yeah.
bad.
It's
for
you,
your
it was you.
Now hold on, how do you do this?
body.
Put it with land.
Hold on. How do you do this? Raise your hand if you know how this is done, not just random thing. You can put a filter on it. Very good. He doesn't have filters yet, but what else could you do?
We use mirrors to like reflect the object to observe it, or
You're very close.
you do it at night.
Can't do it at night. Why? Let's go visit the sun at night. It's cold, right? What is this doing?
Project.
Projecting. What if you took your telescope, pointed at the sun, don't look through the hole, put it in a dark room, project the light on the wall?
Now, whenever you do that, that would make it really hot.
Very close, you're very close. So that's exactly what he did. This is a drawing. So notice these drawings are much better. Right? Because you're not looking at tiny little stars. He's literally looking, this is, his number, and he's drawing it with his hand. And there's enough detail there that you can see not only were these spots dark, they had different variations in brightness. They had definite shapes. This indicated to him that these celestial objects were not perfect. And if you look very closely here, it's gonna be better on the slides when you see them later, or you search sunspot. They look like sunflowers. So the interior is really dark, and they have these petal-like structures. And interestingly enough, he watched these move around like this. He could watch these sunspots move. And they would move across the face of the sun. And that means? No, it's not orbiting the sun.
Sounds real.
The sun is rotating. Pretty cool. Okay. What's the rotation of the sun? That's the sunspot cycle. It's very quick. All right, we'll get to that later. Okay, so no one liked it. That's part of the famous part of the story. So Catholic Church said, no thank you. But he struggled with this because he was a devout Catholic and he didn't quite know how to interpret what he had understood. Did I say it before? Oh yeah. Maybe I'll say it in. So he made this book of all his observations. He sent it out everywhere. We got really upset at him. Because he was able to demonstrate pretty conclusively that in fact we were not the center of the universe, and some people didn't like that. He was formally vindicated in 92. Took him a while to figure that one out.
What's vindicated?
Vindicated means he wasn't wrong. So the Catholic Church said, okay, sorry, we made a mistake. This guy's chill. Right? He hold on, where did I talk about it? Oh god. I don't know if anyway, he wrote this book, and the coolest part about writing this book is that he would send this to all the kings of Europe. Okay? And he said, you don't believe me? I've enclosed a telescope. You go look. And they did. This is how you spread scientific knowledge properly, right? So you repeat the experiment, see if you get the same thing. Here's my hypothesis. I think if you watch, you'll see that these stars around Jupiter, they're gonna go back and forth. If you look for Venus, you're gonna see it has a phase. Go prove me incorrect. And that's the best part about science. Okay, so what have we learned? Ptolemy's model works really well. Okay, for naked eye observation. And then the naked eye observation got better and better and better. And suddenly the accuracy of those epicycles started breaking down. Copernicus thought, well, there's no reason to prefer the Earth. Let's throw back this idea that we had before of a heliocentric model. That worked okay, but it wasn't better. And we needed, in fact, ellipses. We're going to get to the 3 laws of planetary motion. But they all had a model, a scientific model that they would use to construct a worldview and understand, right? And then Galileo said, well, just look at it, please. Oh, there it is, yeah. Okay, any questions about this? Cool. So the process of science, remember, right? You hear stuff like, oh, ask questions, question everything. So what we want to think about that rationally. Okay. If I tell you that the sun has spots on it, you go, you then look up at the sky with your eyes. No, okay. It's good to question things, but let's make sure we do them responsibly, right? We have truths we can agree upon, and similarly, we want to do things without like just saying, "Oh, everyone's a liar, and I'm the only one who knows things." Otherwise, we don't get anything. Okay. So, why was the heliocentric view important, or why do we end up keep sticking with it? I should say. Galileo basically said the heliocentric model is great, right? It describes how the planets move. But we still haven't talked about why are they moving at all. So those are, by the way, are the pictures that Galileo made of Venus. That's the symbol for Venus. He would draw them like that with a different size. Amazing. So detailed. Okay. So what could we possibly use to be like maybe a natural phenomenon to test, for example, lightning?
Like gravity force.
Yeah, so you're saying those words. Imagine we don't have those words.
I want to know why something moves.
Okay, so I want to know how space stuff. What can I use to test my ideas of why space stuff moves?
Maybe like Mark every day about like the direction of something is
What thing?
anything.
So the thing is, you have to remember, look at the sky for like 6,000 years, right? So we know where Mars is going to be, right? We know where Pluto's going to be. No, we don't know what Pluto is. We know where Jupiter's going to be. So the planets are mostly there already, right?
Is it like how maybe like how water drains on like we have like it goes clockwise here, but then in Australia
That's right. Water doesn't do that. No. So that's okay. We're thinking only about space things. What space thing can we use to test? We have a model. Yeah, a comet. Why would a comet work?
Because if they've been tracking comets for a few thousand years and they notice a few of them appear every now and then, they can test if they're traveling the elliptical pattern.
Right. So comets are something that appear sort of randomly. So if I could predict one, right? I saw one come like 25 years ago. If I say, hey, wait 400 years, and if it comes again, then I'm right. That'd be pretty cool, right?
It's here today.
And it's here today. Well, that's 50,000 years. No one was alive for that. Okay, so that's exactly correct. Comets. Comets were initially thought to be disturbances in the atmosphere, like something like wrinkling the top of the atmosphere. But with parallax, which is what, by the way?
how something shifts in the, no, how something shifts in the foreground compared to the background.
Right. So we can tell how far away they are with parallax here on Earth. So I called my buddy in New York and I say, hey, where is the comet for you? With reference to the background stars. And he says, oh, it's in Ursa Minor. And I go, oh, mine's also in Ursa Minor. So it can't be close. Because if it was close, then it would move a lot between those two locations, right? So people were convinced that these things were on straight paths, going in and out. So you could tell me instead, I don't know, this one will come back. And you can believe your ideas about how things move. And so Haley, or Halley, I should say, called Newton up. When I say that, you know that's a joke, right? So he wrote him a letter. And he said, hey, what's up with this comet? 1705. Can you describe what the heck's going on here? And he was like, yeah, don't worry about it. I got a whole law for that. Follows an inverse square law. He's like, what? He's like, yeah, I've been thinking about this for a long time already. The actual correspondence between them was really funny. So he determined that this comet here, Haley 1P, so 1P is the first periodic comet. So this is the first periodic comet, and he was able to determine that it makes and has made multiple passes, both by the Earth and around. So this is a lot of words. Let's see if we can read those without putting ourselves to sleep. This guy up here, giant weirdo. I derive from the celestial phenomena the forces of gravity with which bodies tend to the sun and the several planets. Then, from these forces and by other propositions, which are also mathematical, I deduce the motion of the planets, comets, the moon, and the sea. Okay. This is his claim. He claims that the motion of the planets, the motion of the comets, and the motion of the tides are related. This is his supposition. And he said, I can do this all with one rule, gravity. And then he said, right, this is if you were a Google Scholar, it says, if I've seen far, it's because I've stood on the shoulder of giants. And the giant he meant was Galileo, and the people who stole his. Okay. You want to talk about calculus? That's a huge problem. But anyway, so that's him standing on the top of giants. Okay. Okay. So let's talk about Newton's laws. Everyone has Newton's laws already? Everyone not seen Newton's laws? Okay. So we want to talk quantitatively about the motion of objects that we observe. Right? And we want to talk about why objects fall, how we describe that phenomenon. Okay. So we have this first concept. Oh, sorry, let's go back one. We talked about my emotion. So we're talking about where I'm standing. What are the other things we want to talk about? With the other like physical words? I don't know, when I'm moving, I'm not in orbit, hopefully. What's that? Just describing my motion. Direction would be a part of speed. Speed and direction are velocity and what did you say? Acceleration. Okay, so we got position, velocity, acceleration. Oh, I put time. This is why I can't do my own slides. Okay. Acceleration. There it is. I forgot that time was passing. My watch fucking died today. Okay.
You've not had a good day.
No, it's a bad day. I did that on my other slides. This is a Charles Darwin quote, so I'll share it with you all today. So this is one of my favorite Darwin quotes, which is, for I am very poorly and very stupid and hate everyone and everything. And some days you just have those days. This is a letter he wrote. He went out of his way to write this to a friend. That was the whole letter.
Wow.
How's your day been? For I'm very poorly and very stupid, and I hate everyone and everything. Send. Okay.
He gets it like 6 months later, he's like, oh man.
Yeah.
6
So this one here, position. This one is intuitive, right? Is this one intuitive?
Yeah.
Yeah. right? Okay, what about this one?
Yeah.
What is this one?
Speed.
And what does it mean intuitively?
600 seconds.
Okay, that's the definition. What does it mean
Like,
intuitively?
how fast?
How fast are you going? Right, it's a different word for fast. But it can also be like, you know, am I going slowly or quickly, right? It's the distance over time, it's how much I traverse in a minute, for example. Okay, what about this one here?
How fast is your breath?
How fast is my fast? Okay, so it's too fast. Wait, square. Okay. So acceleration is a change of velocity, right? We're gonna brush up on all this. I know you already have this, but we're gonna make sure. So it's a change both in speed or direction or both. That one I got right. Let's go. Okay. So which of the following which of the following example describes where a car is experiencing a net force? A, the car is making a gradual turn. B, the car is moving at a constant speed. C, the car is stopped on a hill. Or D, the car is floating on a stationary boat. Let me know when you're ready to vote with your fist. Vote on 3, 2, 1. Okay, why don't you turn to someone behind you and ask them what they got? Or, yeah, not in the back row. Just people next to each other seem to all have the same answer, but turn to someone who doesn't have.
I think it's my name.
So, net force, maybe for the force null or something. And grabbing it for the force that's not zero, either you or you just aim or achieve.
Okay, you guys ready? We're ready? Show your fist if you're ready to vote. Vote on 3, 2, 1. Okay, all right, we got a battle here. In these two answers.
What?
Wants to defend their champion.
After the what I am made and would be there's no acceleration.
Okay, let's assume that I don't know what that is. How would you say those in different words?
If a car is making a gradual turn, then it's changing direction at every second,
Okay.
and there's a net acceleration outwards.
Ah, okay, so there must be an acceleration because the direction is changing. Whereas here, is there a direction or a speed change?
No.
No. So therefore, there's no acceleration. And as you mentioned, accelerations are related to
Any direction.
forces. That's what you started with. Okay. Okay. So Newton's first law of motion says that an object at constant velocity, if there's no net force acting upon it, actually discovered by Galileo, but whatever. Yeah. Whoever discovers it second, right? Let's go. So an object at rest remains at rest. An object in motion tends to stay in motion unless acted on by an external net force. And there are in fact forces, right? Currently, this has 2 net forces on it. What are the net forces on it? Normal force and gravity. And the net is this first one, an object at rest tends to stay, sorry, the second one, an object in motion tends to continue in motion. Do we ever see that in real life? Space. No. Everything in space is being acted on by gravity.
Yeah.
But unfortunately, this one's really hard because you almost never see it. The only time you get close is like when you're in lab and you use one of those air tracks. You ever use an air track?
Air hockey.
Last week.
Yeah, air hockey, for example, floats along until you smack it into your opponent's goal and win. Let's go. Okay. Newton's second law of motion. So this is what you just said. That force equals mass times acceleration. Okay. Another way of saying this is that the acceleration is modulated by the mass. That if I press on something and it's massive, it will move less. The small mass, when I press on something, it moves more. Okay. All these drawings are really cool. So this is actually this is actually first noticed by Huygens. And he what Huygens, yeah, how do you say that? Huygens. Huygens. So no, not Huygens. Huygens. So he noticed this for gravity, and he said, I think like the bigger stuff, it's harder to make it go. And Newton was like, I like that, but for everything. Ooh, very cool. Okay. And then okay, that's another way of saying the same thing. I didn't say anything new. Okay. And so nothing happens if the forces are balanced. So a body accelerates when there's an unbalanced force applied. But then, of course, the most confusing one. For every action, there's an equal and opposite reaction. And so if you're here for any of the faculty talks, you've heard about this 14 times, right? Everyone did the same one. Kepler argued that gravity should be reciprocal. So Kepler looked up before Newton, before Huygens, and he said, I think Mars goes around the sun, but I also think the sun pulls on Mars. Wait, I think the sun goes around Mars and Mars goes around the sun. He said, I don't know how they do this, but I'm pretty sure they do. So he argued if the moon pulls on the earth, then the earth should pull on the moon. So this is before tides, before someone recognized tides and the moon actually had a physical connection. So this was, a gravity concept, but it's everywhere. Let's stand on top of that. Pick it up. Work on my hand. Is this something confusing for folks? My favorite demonstration for this law of motion. Somebody have just a single piece of paper.
That one.
Okay. All right. Ready? You demonstrate. Okay, bye. I'm gonna hold this paper like this. You have a piece of paper?
Single piece of paper.
Okay. Okay. So I'm gonna hold on to this. I'm gonna hold on to the piece of paper. Okay, let's demonstrate for everyone. And I want you to hit it. No, I'm gonna hold it. Okay. So you're gonna hit it in the middle as hard as you can. Just like that? Yeah. Try it again. Try it again. Okay. Ready. Did it hurt your hand? You want to go harder? No, wait, ready? Ready? Try again. Ooh, interesting. Was it able to rip? No. It could never rip if I let go of it. Why?
Because there's no force to
No reaction.
track.
Right? You can have that. I know. It's remedial. Oh, you threw it away. Okay. So okay. So the reaction force there could not be as strong as his, like he had a very strong arm going down. When I was holding it, that reaction could be countered, right? Until the strength in the paper failed and it broke. But if I let go of it, then the only thing that can happen is a small amount of force back, and then it moves. There's an unbalanced force and it moves, right? Does it make sense? Cool. There's this cool picture. What's that a cool picture of? Throwing money, yeah. Throwing gold bricks as they go. So no, so this person has bricks and they're on like a, what are those called? Yeah, that's a skateboard. They got a bunch of bricks on a skateboard, as we all do. And you're just tossing bricks to get away.
Scary.
To go fast.
To go fast. Right?
Too much fire. Too much fire.
What is this an example of?
All the bricks.
So they can move them. Start them.
You've seen it already today. What principle uses this? Obviously not a skateboard.
Oh. New start off. Oh.
Yes, this is Newton's third law. Good. Which principle actually uses this? Who does this to get around? Rocket ships. Rocket ships are just skateboards with bricks. So all you have to do to do rocket ship is this. Ready? You see it?
Yeah.
Wait, what?
Ready? Watch. Ready?
What?
Tilt your head and look at the same picture.
Oh,
Oh. So this is us in the rocket ship, and we have bricks in our rocket ship, and we throw them out, and as we throw them out, we go in the other direction. And in fact, that's exactly what we have. Let's go. Okay, so what's that thing there?
Rocket.
The shuttle, very good. And these are solid boosters, and it's pushing out gas at very high velocity. And because there's an equal and opposite reaction, it pushes the spaceship up. Okay? In case you didn't believe it. Yeah.
So is that why rockets have a bunch of like modular pieces that fall off?
Yeah, but why do they do that?
They need
Sort of.
more,
Wait.
like, they can, so they can go up higher.
One at a time.
You're reducing your mass, so you need less force.
Yeah, so we drain this, right? And then you let go. Is that what you're saying? Yeah. Yeah, so as we go up, action, reaction. And as you get rid of this stuff, now you have the container. Throw the container away.
Where the container go?
That is.
Where does the container go? Good question. Some of them do. But let's say these ones down here. They fall in the water. And then they go to the bottom of the water. And we don't get them back. So this is why people like SpaceX, because these are reusable launch vehicles. So these solid boosters come back and they sit back down on the ground, and then you fill them up like you fill up a car. No, not like that. Tesla doesn't use anything before it. Okay. These make sense?
Yes, sir.
Yeah.
This is what we'll need. Internalize it for orbits. And then we're gonna immediately move away from it. We're gonna talk about planetary geology. Okay. Let's talk about gravity. All right. All objects accelerate at the same rate, at least here. Ooh, it's big gravity. No. Okay. So for astronomers, these are the right numbers. 10 meters per second spread. What's the real number? 9.8. Not in this class. Okay. So what does that mean? It means if you start at the top, you throw a ball, velocity can be 10 meters per second. Okay. 2 seconds later, it'll be 20 meters per second. And it continues. 10 meters per second. Okay. So I made this claim, and then I dropped the balls wrong. So it's fake, right?
yeah.
Yeah. So all objects fall with the same acceleration. What about a hammer and a feather?
Same thing.
Yeah,
You know the answer, don't just say it all. So what happens to a hammer that doesn't happen to a feather?
Air resistance. It doesn't catch as much air resistance.
Doesn't catch as much air resistance, which means what? Doesn't fall faster, right? So thank you for the paper. And which one hits the floor first?
Ball. Tennis ball.
You sure?
oh,
Well, the way you're gonna.
Which one?
Tennis ball.
Ball? Oh, damn it, okay. Alright, well, what about this? What about this, Brendan?
oh, thank you. Well, not one back. Yeah, it's like-
I lost my answer there.
like a ball.
So.
Slow.
Pretty close. Still not good. Okay, what about this? Oh shit. I have a different demonstration on
What about the laptop?
Monday. Just drop the laptop. Does anyone have a book?
Have this binder.
Yeah. But it's better with like a hard.
Well, I have the.
No, I have a weird book right here. that you can even-
Oh, thank you. Yeah, that's perfect. Okay. Have you ever seen this demonstration? Sorry. No errors, right? So once the book is going, this folds just with it. You got a little moon laboratory right in your hand. Thank you. So of course, we went to the moon. Do not argue with me about this.
Did it.
And they were like, well, let's prove it. And so this is really fun. Apollo 15, they bring a hammer and a feather, and they say, let's show that they drop at the same time.
Tim, we copied both solar wind and penetrometer drum in the ETB.
This is on.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. I have a good picture there. I've got
Beautiful picture, Dave.
Left hand here.
well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? How about that? Mr. Galileo was correct in his findings.
Watch him try to get it. Okay.
Tim, we copied both.
Okay. So, let's see, is this everything I wanted to say today? Every action has an equal opposite reaction. Why can't a paper hold a piece of hammer? We already saw that kind of with his hand, right? That it can't provide that same force back. And then this is my fun. I tried to put these comics in. They intro astrophysics. So it's like, how do they know how to load units on bridges? They just drive bigger trucks until it breaks. Then they made a last truck and rebuild it. Of course, not how it happened. And it's just remember, not all sources of knowledge have the same level of accuracy. Okay, so we're gonna be a little skeptical when we read certain things. I'm of course perfect, but not this dad, right? Okay. Let's talk about motion in space. What's that? What is that?
Satellite.
Hubble. The Hubble Space Telescope for you. So this is a telescope. Its entire life is just chilling. Out here is where it does the looking. And over here is where it does the telescoping. And then it sends it back down to us. Okay. It's in orbit around us. So that is the Earth. There are no propellers. Yeah, this is definitely, that's a little radial antenna to send us data back. Why are there no propellers?
Because it's in
It's in orbit.
Yeah.
Okay, just saying that, but hold on, one at a time. So why is there no propeller?
Well,
But it's needed.
When I say one at a time and then everyone talks again, just raise your hand.
because they would continue going.
Okay,
If there were propellers.
so if there were a propeller, what would it propel off of?
Nothing.
Nothing. So propellers work on Earth because they push air by you. They don't work here because there's nothing to push.
But like, it does change the direction it floats, right? Is it,
There are no propellers on a spacecraft.
no, I know,
Oh, yeah.
but like, it can look in other directions besides that one direction. right?
Oh, yes.
That's what I mean.
So interestingly enough, it has what are called reaction wheels. So if you want to point somewhere, what you do is you turn a wheel. And the fact that there's conservation of angular momentum means that you're going to point in the other direction. No, weird. So in fact, this thing goes around the Earth, right? Every 90 minutes or so, like this. And we can have it point to the same place just by slowly turning these three wheels. One wheel's like this, one wheel's like that, and one wheel's like that, and that gives us full autonomy in pointing the
Is it
spacecraft.
always spinning or are they?
Yeah, so they're not always spinning, right? It stays with some rotation. But for example, we could counteract any spin by rotating them, spinning them up and spinning them down. And this is how we move all spacecraft.
How old is that? How long is it?
Very old.
So is it like using like an old printer?
What?
Like for like the people, like the data when they get it.
No. Data technology has not gotten better.
No?
No, think about it in this context. What do we want from this telescope?
Pictures.
Good. Has picture technology changed dramatically?
No.
No, it's just numbers, just how much light am I getting in this pixel versus this pixel? That hasn't changed. Now, is JWST much better? Yes. Why is it much better? Well, it's bigger, collects more light, better, it does doing what it does, right? So you fly something in space, you're already a lot better because you don't have the atmosphere blocking you, and we'll talk about that when we talk about telescopes. But the bigger you can be, the better. Bigger is always better in space.
But doesn't it have to track it from the way they get the space?
Yeah, so this is what I'm about to talk about right here. So, in fact, you can see down on the Earth, these are what? Clouds, very good. And this here is the edge of space,
Scary.
or the transition from the bottom of the atmosphere where we like to live to the top of the atmosphere,
What a man.
where this is, several hundred of kilometers up. But there's still a tiny bit of atmosphere that's bumping into us and slowing it down. And so you have to keep raising it up. Otherwise, it'll fall down and burn up into the atmosphere.
So if that takes pictures, how does that picture get taken?
Good question. How did they do it?
Like a survey with a camera.
Yeah, with a camera.
Oh, it's fake.
How do they do it?
Well, we need twice service.
We have astronauts. That's around space. We've been in space. That's close compared to how far we've been in space. Right? So you just drew in your lab how far we've been. Right? You showed that we went to the moon. Okay, so think about the Earth for a moment, the size of a basketball. How big is the atmosphere in those terms? A sheet of paper. Papers were really popular. Okay? A sheet of paper. So getting from a sheet of paper up, easy. We do it all the time. Going up to fix this, yeah, it was annoying, but we had to go fix it because the mirror was broken. We launched it, we looked at it, we were like, it's blurry. Damn it. So we flew up to go fix it. Okay. Okay, so we're gonna talk about how we describe motion in space. We're gonna talk about what laws control that motion, and most importantly, how do we create and store energy? Okay. Okay, so suppose you lived on the moon, which of the following would be true? A, your mass would be less than on Earth, but your weight would be the same. B, both your weight and your mass would be less than they are on Earth. C, both your weight and your mass would be the same. D, your weight would be less, but your mass would be the same. You know when you're ready? Let's vote on 3, 2, 1. Okay, got almost everyone. Why is it your weight would be less, but your mass would be the same?
Because there's less gravity.
Right? What do these words mean?
So weight is a measure of like force, like a force. And then mass would be like the amount of stuff you're making.
Right, so F equals MA. So you have an A piece there, you have an M there. So the M is the mass, and like you said, the F is the weight. Okay? Okay. Oh wait, do I want to talk about this? Yes. Let's talk about this example, but I think you're gonna get this. At exactly the same time that you drop a glass, your roommate throws a bottle perfectly horizontal at your instructor. Okay, the bottle lands at the feet of the instructor. Which lands first? The glass or the bottle? Is it A, the glass, B, the bottle, C depends on how hard you threw the bottle, or D, both at the same time. Let me know, put your fist up when you're ready. Someone's like sidearming it, and someone's dropping it. Okay? Just chuck it at me, someone drops it. Perfectly horizontal. And it's gonna land right here. Which one lands first? Let's put it on 3, 2, 1. Okay. We got half for glass and half for both at the same time. Anyone want to defend this? Yeah, in fact.
Horizontal motion is independent of earth motion.
Oh.
They land.
Interesting. So we can separate these motions. They're vector quantities and they don't interact. Well, let's show that. Okay, the glass is going to fall and the bottle is going to go to the left. Glass doesn't go to the left at all. And then you drop them. That's the same. So the timing is the same. Right? And so the harder you throw it, the farther it goes. But only horizontal. So where am I headed with this? Orbit. Orbit. So you keep throwing it very fast, more than it falls down. Okay. So let's imagine you start on a very, very big hill and you have a cannon. Okay, and you want to shoot, who are these people? Someone in the middle of the Atlantic. Atlantic? Are you in the Atlantic? All right, so this ball goes here and it lands. But if I want to shoot even farther, like these, I want to start some ruckus in the Middle East, right? Then I would have to shoot it so far that the earth itself fell underneath, right? And eventually I can shoot it fast enough that it's moving more horizontally, right? For every amount that the earth itself drops underneath. So you could have them move like that. That makes sense? And then it could hit me back in the head. Okay. So this is the idea of what an orbit is. Objects are falling constantly around the earth. The idea of free fall doesn't mean there is no gravity. Right, this is one of the common misconceptions people think about. Oh, they're floating, there's no gravity. No, there is gravity. You're all just falling at the same time. Like being in an elevator, and all your stuff flows in front of you, and then you on the ground. Okay. What happens if you let go of this ball? Does the string move along the path A, B, C, D, or E? Put on 3, 2, 1. Okay. Why is it C?
Because first it has to go horizontal.
They keep
Hold on. First it has to go horizontal. What do you mean by that?
It still has like the motion of you spinning it
Mm-hmm.
before.
Yeah, so here it has some velocity. And if I let go of it, what happens? It keeps going straight. Because objects in motion remain in motion in the direction they were going, right? Very good. So I was providing a force to pull it back in, right? So this force is oriented in towards my hand. Okay. What keeps an object orbiting? The force pulling it back towards the center and curving the motion. The speed itself isn't changing, right? The gravity is still pulling it radially. Okay, so we know that there must be an acceleration, we know there must be a force, and gravity is that force. Okay. What does that force look like? Functional form? Force of gravity equals? Very good. All right, you're gonna memorize that, right? Just this one. Body 1, body 2, some distance between them. This one pulls on this one pulls on that one. G, don't memorize that. Always copy it. Okay. We're not gonna talk about that. Do we know this one? Gravitational force exerts on you the same that you exert on the earth. Why doesn't the earth move when I jump? Raise your hand. Yeah.
Because of the larger force.
The force has to be the same, right?
Or-
What does that mean?
or-
The mass of the earth is greater than your own mass.
Right? What does that mean?
Because it's from gravity.
Gravities are the same, right? We just said that they have F equals ma, they have to be the same. How come we don't see the earth move?
Takes more force to get the same acceleration.
It's the accelerations that we see. We don't see forces. We see what happens to them. We see the motion, right? The whole earth is not going to be pulled very much, but in fact, it does pull, it's very, very small, like 10 to the minus 23. All right. Oh, that's it. What else? I didn't put enough slides in here. Okay. So let's see, what are we gonna talk about next? Let's pull up these next slides. You're not done. You're not going anywhere. My goodness. There we go. Relax, I just didn't make them. They're still here. Okay. We said that. I put Darth Vader on them. Anyone know?
Using the force.
Of course, yeah, okay. Fucking dork. I get it. Okay. So let's compare some distances here. We want to remember that we can use these, and we're mostly going to do these in ratio. So this is the level of math that I will expect from you in this class. It's not very hard. It's not calculus. There's no computers. Well, there are computers, but you don't have to use computation. Right? So I'm going to move Darth Vader from the surface of the Earth to 2 times as far. I want to know the ratio of the gravity. 1/4. Okay. Why is that? Inverse square law. So let's do that in detail. There's GMM over R squared. And M's aren't changing. This D is just 2R. 2R squared is 4R squared. Cool. Good stuff? Okay. Uh-oh. So many steps. Okay. Hold on. Let's just move to this part here. This is the part I want. Okay. So far we're talking about the force of gravity. And the stuff that I really care about is the acceleration, right? So here's a cabbage, and I want to know how fast the cabbage falls. So I can do F equals ma, and I can cancel out that m of the cabbage and do this nice little math. So hold on, where is it? God, I put too many steps in here. It's 9.8 meters per second. Now, what's that real number?
10.
10, very good. 10 meters per second squared. Okay.
That's the real number.
What about on the moon?
1/6
Of what?
Earth's gravity.
Earth's gravity or Earth's mass?
Earth's gravity.
Well,
We set it up like that. You set it up like that. And it's 1/6. I don't do that. So of course the mass here is 81 times more massive. And the size is only about 4. Is that what you're talking about? Density. What does density tell you about sizes there? If something's twice as large, what happens to, say, the radius in volume? Cubed. So it has 8 times as much carrying capacity. Right. Okay, so let's talk. I don't care about that. Okay. So how fast do things orbit? Very fast. Very fast. Okay, let's see if we can calculate these things. So we need some words really quickly. Orbit and then orbit T. General will say stuff like satellite, and I'll assume that you know that. You can use Newton's law of gravity to calculate how fast they move, and it's like that. How did I get that so easy? Google. What am I equating here?
Where's the mass of the orbit?
Mass of the orbiting. What things am I equating here?
Circular motion.
Yeah, circular motion has what form? Oh, this is the worst chalk. What is that? Well, if you stop rubbing your eye. Okay, what about this one here? What's the circular motion equation look like? Right. Oh my god. I'm just too strong for that chalk. I guess that's the problem, right? Oh, don't answer that. Okay, so here we have. Ever seen that?
Is that an A or a U?
It's a V.
Wait, what? That's a V?
Okay, you guys, come on. I'm so cranky just because it's what, past your bedtime? Let's go. V squared, you ever seen that? Really?
Yes, yes, I have. I have.
I've never seen that.
Raise your hand if you've seen this before.
Seen it in high school.
No?
No, I've never seen.
It's in the book. I'll show you. This is it's just what you have to know. If something's moving in a circular orbit, if something's moving in a circle, including that ball, you see that ball going around in a string, if it's moving in a circle, this has to be the acceleration. Yeah, v squared over r. And so if you set that equal to your GMM over r, you'll see that you get v. Because I have a v there, put the r on the other side, take the square root. Cool, yeah.
How is the R on the bottom for that? When you times the R?
It was squared on the gravity.
It's squared, remember? You only get one of them. No?
Yeah.
Set them equal? And get one of them? That could be a V, guys. I don't know why you don't like my drawing.
Wait a second.
It's not.
Okay. Alright, I'm gonna cry about this later. Okay, so an astronaut and a camera are floating outside the space station. Which moves fastest? Is it A, the shuttle has the greatest speed due to the greatest mass? B, the astronaut experienced the greatest acceleration since they just exited the space station? C, the camera speed is fastest due to the lowest mass? Or D, they all have the same orbital speed? Show me with your fist. 3, 2, 1. And from the answers, I'm getting mostly 4s. 4 is correct. Why is that? No, it's correct. Correct. 4 is correct. Because, of course, here, this is only of the object you're orbiting. Does not depend on the thing doing the orbiting. It's only a property of the thing that we are orbiting. This would be very dangerous if it weren't the case. If I stepped outside and the camera started flying away, everyone would be screwed. Okay, we'd never be able to travel in space. Okay. So it must depend only on orbitee and the orbital distance. All right, that got me far enough. We can talk about the rest of this later. What's the average speed here? Just guess. 17K what? Miles per hour? Meters per second?
17,000 kilometers.
70,000 kilometers per hour? Oh my goodness. It's about 8 kilometers per second. Or 18,000 miles an hour.
It was faster.
That's right. Yeah. Okay. Okay, thanks, folks. I'll see you on Monday, and then we'll do a lab Monday evening, hopefully at the observatory. So for the observatory, remember, it probably will be cold. So if you have hats and jackets, that's what you want to wear. If you have your homework, please put them here. Thank you. What do you think? I'm made of staplers?